This video, I'm going to show you how to implement the first fit algorithm for memory allocation, or I should say contiguous memory allocation. I'm going to show you the C code, and then I'll explain how to test the algorithm and find out the average memory utilization for it, and give you a few more hints on how to implement a similar algorithm like next fit, best fit, or worst fit. What we are going to do here is um, to create a test bench or a simulation platform for any of these algorithms. The way this platform works is that uh, you have to start with a very long array of integers. We call that the physical memory. And then after that, we are going to randomly generate a bunch of requests for memory. And we try to satisfy them in a first come, first served manner. If a request fails, then we release a random block. And we do this again and again. In order to uh, represent uh, occupied blocks in this simulation, we use a structure like this. Imagine you have an occupied block of size 6, which satisfies a request of size 6. What we do is we grab 10 bytes or 10, I should say 10 integers, 10 contiguous integers in our long array representing the physical memory. And then we store the following values in that array of size 10. The first cell of that array of size 10 will store the size which is 6. The second one and third one are dummy values, which I'll tell you why we use these dummy values here. And then the next 6 elements are going to be the data that we're supposed to store in the in this array because we're satisfying a request of size 6. So we assume that there exists some data of size 6. And then at the very end, we're gonna write down the size again. And this way, we can structure an occupied block. In the case of a hole, which is the opposite of a occupied block, that's basically a released block. Or initially we have a very large hole that covers the whole memory. But in the case of a hole, if you want to represent the hole in your simulation, you need to store it this way. The very first cell and the very last cell of a hole or a block that represents a hole will store negative numbers. That negative number is the negation of the size of the hole. So imagine the block I showed you earlier is going to be released, right? We're going to free that block. It's going to create a hole like this with size -6 because it's a hole, so we negate the size to specify that this is a hole, not an occupied block. And then the second and third element of that hole would be the address to the previous hole and the address to the next hole. The reason we have to store these is because we keep track of all the holes in the form of a doubly linked list, which happens to be circular as well. And basically, I mean, this is the data structure to store the holes. And then later we're going to use that data structure to basically find the next hole using the current hole or find the previous hole using the current hole. So this is a data structure that is commonly used for implementing the contiguous memory algorithms, strategies, or algorithm like contiguous memory allocation algorithms like first fit or next fit. Other than these two structures that I mentioned, we pretty much have no other structure in this simulation platform except a list of blocks, which I'm going to show you when I go through the C code. One more thing you need to remember is that the size of each request, which is represented by S, is a random number from a truncated normal distribution with the mean equal to D, standard deviation equal to V. The minimum value of this truncated distribution is 1. You cannot have a request with less than one size, which is obvious. And we assume that you're not allowed to have requests as large as n-1. So anything greater than n-1 is not allowed. So we're going to truncate that. We're going to discard that. This is only for, random number generation when you're trying to simulate the size of or generate the size of requests that are going to be satisfied in a first come first serve. And that's pretty much it. After that, we are going to run this algorithm, or I can call it a pseudocode. We're going to repeat x times, where x is one of the simulation parameters, the following procedure. The procedure starts with choosing a random number and requesting a block with that random number. The random number should come from the distribution that I mentioned. And make those requests, and for every request satisfied with the occupied block until a request fails. Why does it fail? Because you don't have enough memory anymore, because the size of holes are too small for the next request, so no hole can host the next request, so that's why it fails. When it fails, you're going to record the current memory utilization, which is a ratio of all the or the total size of occupied space divided by n. That's the ratio we call it memory utilization. Then you're going to randomly select an occupied block, and then you release it. Releasing that is going to either create a hole, or it's going to make an existing hole bigger, because you're coalescing the release block with an existing hole into a bigger hole. So that's how it happens. You're going to repeat this scenario X times. And at the very end, we're going to calculate the average recorded memory utilizations and then average number of holes when satisfying a request. And that's pretty much the flow of your simulation. What you need to do is to implement some or all of these strategies. If you want to get extra credit, you have to do like all of them, and then or 3 of them. But if you don't want to get extra credit, only 2 of them are enough. And then you have to run the simulation 4 times for each of these 4 sets of parameters. The values of n seem to be very long, but these are basically powers of 2. This is 2 to the power of, if I'm not mistaken, 24. This is 2 to the power of 28. And this is, let's say, 2 to the power of 16. I'm sorry, 26. This is 2 to the power of 18, I guess. Yeah. So this is the power of 16. so on and so forth. So these are powers of two. The reason you see these big numbers is because, these are powers of two. And at first, I set these parameters to bigger numbers, but I realized that when you're trying to run it with Ocelot, you may get to some low memory errors, and it's going to cause you a trouble running them. So I said, let's scale it down and try with the smaller values. All right, and then the deliverables would be a README file with the name of the team members, a report that contains the two tables, which I'm going to show you next, and all the source files for your simulation. The tables that you need to include in your report would be these two. The first table is tabulating the average memory utilization numbers for the 4 different scenarios and the 4 different algorithms. And then the second table will tabulate the average number of examined holes under the 4 algorithms and the 4 scenarios. So you have 16 numbers here, 16 numbers here, is total 32 different numbers. If you want to do all the algorithms, otherwise you're going to do half of them. If you don't want to get extra credit, you do half of the algorithms. All right, let's look at the C code. I have a C code here. It's a little long, but it's very easy to understand because I have broken the code into multiple functions. I'm going to post this on Canvas. You can take a look at it. And then I have a header file called allocator.h, and I have a first fit.c, which implements the first fit algorithm. I'm going to tell you what you need to do other than the given code. So let's take a look at the allocator.h. This basically defines the block structure, which is made of 3 numbers, a released, which is a Boolean. It's a binary value. It's either 1, which means your block is released. 0 means it's occupied. Address, which is the index of the first cell in the memory array that represents, it's the first cell of a block that represents your block, and then the size is the size of the block, excluding the 4 cells that are used for metadata. The metadata is those 4 bytes or those 4 integers that I mentioned earlier. The first 3 cells and then the final cell. The first cell and last cell both contain the size of a block, and then the second and third cells will store basically the address to the previous hole or to the next hole if your block is already released. And it's going to have some dummy values if your block is not released and has some meaningful data in it. So in other words, if it's occupied. That's your block, a type definitive block. And then I have an external array of blocks with the size of 1,000. This should be good enough. I have a maximum n, which is 10 to the power of 28. That's the maximum n you need. You don't need more than that. And I have an external array of integers called memory with this size. This alone can, this alone requires 1 gigabyte, which is a big number, right? So I just want to tell you this is a heavy program because it consumes a lot of memory here. Also, I have a number of examined holes because later I'm going to use it to find the average number of examined holes for a scenario in your simulation. And then I have an array of next request, which is filled with a number of normally distributed random numbers that represent the sizes of different requests. The requests are placed in a chronological order. That means you need to first satisfy the request at index 0, then 1, then 2, then 3, all the way. to the end. And then again, the maximum block count is 1,000. You're not going to use all 1,000 blocks in a scenario. This is too many, but I just wanted to be 100% sure that you don't need more than that. So I just set it to 1,000. And then there are some function signatures that I have placed here to declare the functions because I'm going to use them in different um, files, and that's pretty much it. That's basically our allocator.h. Remember nrand from the previous assignments. That's a macro to define a random number generator. I'm sorry, to generate a it's a macro that generates a normally distributed random number with the mean equal to 0 and a standard deviation equal to 1. Error is just a macro that prints something on the standard error and then exits with a non-zero code. That would be for fatal errors that can happen in your program. And that's pretty much it. Let's look at allocator.c. I'm going to start with the main, obviously. So the main is pretty simple. We're going to first handle the arguments. In the handle arguments function, I have made sure that the user doesn't place less than 9 or greater than 9 arguments. If it's not equal to 9, I would say you have too few / too many arguments. Forgot to say many. And but I expect the user to enter a sequence like this: dash n number of the memory size dash d, the request size mean, dash v, the request size, the standard deviation, and dash x, the number of rounds in your simulation. And then in this while loop, I will basically initialize the values of n, d, v, and x based on the argv values. And that's pretty much what this function does. After this function returns, we are going to call this function, generate all request sizes. That's nothing but a for loop that goes 1,000 different iterations. In each iteration, it generates a normally distributed random number. It rounds it to an integer. And then as long as that integer that is the result of the random number generator is less than 1 or greater than n minus 9, it's going to try again. If your request size is in the valid range, then it's going to get out of the do while loop and it's going to store it in the external array of next request at index I. And then this is basically the definition of that external array. After the generate all request sizes return, then we are going to call this function, simulate first fit. Of course, you need to have another one for next fit, another one for worst fit, another one for best fit. I'm going to only show you the simulate first fit in this short video. Let's get to the body of the simulate first fit. It's going to be in the other C file called firstfit.c. I'm going to post this on Canvas as well. Let's see how this looks like. We're going to first print out, we're going to simulate first fit. That's the beginning of your simulation. That's a message just to tell user what's going on. And then what you will do is start your memory with a very large hole. You say memory at index 0 and memory at index n minus 1. Remember, n was the capacity of your memory that doesn't exceed 2 to the power of 28. So you say the first and last cell of the memory should be equal to the negation of the size of the hole. Remember, the size of a hole should be always negative. So you need to negate the size of the hole. The size of the hole is n minus 4. Why minus 4? Because 4 cells are already used for metadata for storing the previous hole pointer, next hole pointer, and the sizes on the first and last cell. other than storing these size negations in the first and last cell of the memory, you need to also store 0 at index 1 and 2. Why 0? Because at the very beginning, when you start your program, there's only one hole. Therefore, if you think of a double linked list and you have only one node in your linked list of holes, that node or that hole refers to itself in its previous node, in its previous pointer and next pointer. So that means the head of a linked list dot next and dot previous would be the same as the head when you have only one node in your linked list. So that's how your linked list is initialized. Then you basically have to initialize a few other things like how many blocks released or occupied you currently have. You have none because this is just the beginning of the simulation. And then the total number of occupied size will be 0. That's going to keep track of the size of blocks that are currently occupied. The reason for this is because it's going to make it much easier when I calculate the average memory utilization. Then I have a double average memory utilization, which is going to initialize to 0, and then it's going to keep adding the total occupied blocks over n ratios over time, and then at the end, you're going to divide it by the number of rounds. I'll show you how it works. We have number of examined holes initialized to 0. Why do we initialize to 0? The reason is if this is not 0, we have to reset the counter. That's a counter that you have to keep track of how many holes are examined by the first fit algorithm. And then in this for loop, I'm going through X different rounds. X is the parameter passed by command and arguments. I is going to be the index of the next request. I is going to keep incrementing as we go forward. In an infinite while loop, we start getting the first request or getting the next request, I should say. I hear printf just to show you on the output the flow of the simulation. Trying to satisfy the request with the size equal to next request bracket I. I is initially 0, but it keeps increasing. And then I call the find first fit, which I will show you later. That's pretty much the function that you need to change if you want to create, let's say, next fit or best fit or worst fit. This is the key difference between the four memory allocation algorithms that I mentioned before, because this function is the one that selects one of the existing holes to satisfy the given request. If you change this, your algorithm will change. If you change it to, let's say, finding the largest hole that is appropriate, that would be worst fit. If you try to find the smallest appropriate hole, that would be best fit. Or if you do the next one, that would be next fit. So here I'm going to start from the beginning of the memory and then find the hole with the lowest address that can satisfy the request that is equal to the next request I in size. After you find the first fit, that's going to return a hole address or the address of a hole that is big enough that can satisfy your request, or it's going to return -1. If it returns -1, that means your request failed. We're going to break out of this while loop and we're going to do other things, which I'll show you later. But if it doesn't return a negative number, that means your request has been granted. So we are going to occupy a block of size, block size in the hole that starts at this address. And we are going to find out the block size, which is going to be next request I, and then we're going to increase I so that in the next iteration, we can refer to the next request because this request is already granted, so we need to increase I. I is a counter on the list of requests. And then this occupy is going to occupy a block. And after this function returns, we are going to increase the total occupied size by block size because we have successfully occupied the block. As I told you, this while loop continues until the request fails and we break out of it. Then we are going to update our average memory utilization. You need to add this by total occupied size divided by n, where n is the memory size, and this ratio we called memory utilization. After you do this, you can print the current AMU. That's not going to be the final one. The final one will be printed at the end. You can get rid of this. This is just for me to show you how a demo of how this can be executed. Then you specify a block to release or a block index to release it because as I showed you in the pseudocode for simulation, after a seek request fails, you need to release a block. So I have created an integer called to be released block, and I have randomly chosen an occupied block to release by calling rand and then getting the mod block count. If that number represents a block whose released flag is on, that means I have chosen a block that is already released. So I cannot release it again. Therefore, I need to try again. So I put it in a do while loop and I try to, choose another random number and then see if that one is released or not. And I do this until at some point, I find the block that is not released yet. It's already occupied. So I can say, let's release it. Right? Here again, I print this message just to be user-friendly. You can get rid of it. And then you can also even print the whole set of blocks. I have this static function, if you want to look at it. It just prints all the blocks in a user-friendly fashion, just for you to see what's going on. I mean, this is just to show you the current occupants of the memory. You don't need that. I just commented that out because I don't want to have a very long output on the console, but you can bring it back. So after you do this, then you're gonna release the block that you have chosen by calling the release function, which I'm going to show you later. Then you need to say the total occupied size has to be decreased. Why? Because you just released the block, so the total occupied space would be now less. How much less? This much less. The block to be released, dot size less. And then again, you can even print your list of all blocks after you release one of them if you want to do some debugging or if you want to see what's going on in your simulation. After this for loop ends, after you do X rounds, then we're gonna print the average memory utilization in the form of a percentage with 2 digits of precision. All we need to do is to multiply 100 by AMU and then divide it by X. And that's gonna give us an average over all different rounds. And then the next thing we can do is the average number of examined holes in the first fit algorithm, which is again represented with a 2-digit precision. All I need to do is to get the number of examined holes divided by X after casting X to a double. And that's basically how to generate the final tables for your report. Now that you see this simulate function, it's time for me to go through the functions that are called by this. The very first function that we called in the simulate first fit is the find first fit function, which is the meat of the algorithm. That's the reason we call this first fit. How does it work? We are going to go through the linked list of all the holes and find the hole that is big enough. We're gonna start from the beginning because it's called first fit, so you need to find the very first hole that is big enough with the lowest address. So let's set the current address to 0. That's just a pointer to the first hole, and the number of examined holes should be increased because that's when you're looking for a hole. That's when you need to start counting how many holes you have visited. The way this simulation has been designed enforces the following fact. The fact is always the block is starting at address 0 is a hole. There's no other way possible. And the reason I made it this way is because it's going to be much easier to deal with a linked list of holes with the head starting from index 0. So that means the double linked list of holes has one member that is always stored at index 0. That means you're beginning your memory with a hole, right? And it's not hard to prove it. I don't want to go through that, but just remember that. But just to be a little sure, I have created this while loop and show you that even if the first hole is not at the beginning, you can go through this while loop and find out the first hole. You can say while memory current address is greater than or equal 0, that's the sign that your block is not a hole and it's an occupied block. If its first cell has a non-negative number, that means it's not a hole. Then you need to change your current address. You need to increase it by the size of the current block plus 4. 4 for metadata. Memory of current address is the size of the occupied block. And then if the current address goes out of bound, then you return -1. -1 means your request has failed. This is basically just to find the first hole. Again, this while loop always will never get executed, but I just wanted to place it here so you can see how to find the first hole if the first block is not a hole. But this is kind of useless. Let's go forward. After you find the first hole, which is going to be the current address, it's time to go through the linked list of holes and find out the very first hole that is big enough. How do we do that? The size of a hole is calculated this way. It's the negation of the content of the very first cell. If that number, if that quantity is less than the request size plus 5, then we're gonna try again. How? By, we're gonna update the current address. Why? Because we're gonna move forward to the next hole. So my definition of a big enough hole for the current request is that the size of the hole should exceed this much. Request size plus 5. Now you may say, why did you add 5 to it? I want to leave at least 5 byte extra room for the remaining hole. I don't want to fill out the hole completely, just to make things simpler. So don't touch this in your other algorithms. Also, if you want to check whether a hole is big enough, always leave 5 byte of room, because that's gonna make things a lot easier for you. Because when you occupy a hole with this request, that request cannot fill it up all the way. you always have some little room for a tiny hole that remains from the original hole. So that basically allows you to make things simpler, and you don't remove a hole. So when a hole is created, it's not going to go away. It's going to always remain. The size can shrink, but it's not going to go away, and it's going to make your life 10 times easier. So always remember, this is how you find out your hole is you find out the hole is big enough for the request. In that case, if it's not big enough, then I have to increase the number of examined hole by 1, because I'm going to examine another hole, and then I'm going to set the address of the next hole equal to memory current address plus 2. Plus 2 was the address of the next hole. If you say current address plus 1, that's the address of the previous hole, but current address plus 2 will be the address of the next one. And basically this way, in the next iteration of the while loop, current address points to the next hole. And then here you need to make a check. You need to check whether the next hole is equal to the first hole. If the next hole is equal to the first hole, that means you have examined all the existing holes and none of them are big enough. So your request will fail and you return -1 immediately. But if you don't return -1 and this while loop at some point gets terminated because the condition is false, then you have found the big enough hole, so you return its address. This is the first fit, find first fit function. The second function that I called in the simulate first fit, other than print, is the occupy and then the release. So I'm going to show you the occupy function first, and then I'm going to show you the release function. So I'm going to show you these two, and then that's it. That's pretty much the last thing I'm going to mention in this video. Let's start with occupy. When you want to occupy a block, you have 3 input parameters. One is the block index, which is going to be the current block count. That's the index of the block in the array of blocks that we store, all the blocks. And then you also need to know what's the size of the block that you want to occupy, and what's the address of the hole that is going to host your block. So it's a whole address, block size, and block count. The plus is going to increase the block count for the future. But let me show you the occupy function. This is the occupy function. You get the whole address, block size, and block ID. I call it block ID, but it's basically the index of the block in the blocks array, in this array that is defined in line 5. How does it work? Basically, you have to shrink the size of current hole so that it can host your block with this size. In order to do that, in order to shrink the size of a hole, you need to first find out the original size. The original size of the hole is negation of memory hole address. Then you need to calculate the shrinked value. So when the hole gets occupied by a block, the size will shrink to the following value. Then the new hole size will be hole size minus block size minus 4. Why minus 4? Because every block needs some 4 cells for the metadata. Then after you find the remaining hole size, which is the new hole size, then you can calculate the block address. I'm going to place the block not at the beginning of the hole, but at the end of the hole. Why? Because when you place it at the beginning of the hole, then you're basically changing the address of the hole, and then you need to go to the linked list or to the previous and next hole, and then you need to update the address of the current hole in the previous hole and the next hole. That's a lot of headache. So in order to avoid that, your block is going to be placed not in the low address of the hole, but in the high address of the hole, in the end of the hole. So that's why the block is placed in the following address. The block address would be whole address, the beginning of the hole, plus the hole size, the new hole size, plus 4. So after the block is occupied, you have this size, and you need to add 4 because the hole needs 4 cells of metadata. After you do that, then you need to update the hole size, which is going to be equal to the new hole size. The first cell of the new hole would be hole address. The last cell would be the block address minus 1, because it's going to be the left neighbor of the new block that you're occupying. And then you have to place the block size at the beginning and end of the block, because as I said before, your blocks should store their size at the beginning and then the last cell. This is the first cell, and this is the very last cell. After that, you have to store the new block in the list. Because the blocks array is going to keep track of all the blocks, you need to store it there. Blocks at index block ID that released is 0. That means it is occupied, it's not released yet. The address is equal to block address, the size is equal to block size. And that's it. That's your occupy function. Don't change that, leave it there. The release function is more complicated, but I have broken it into multiple functions like add hole, left coalesce, right coalesce, and double coalesce. So it is easier to understand. The way it works is that, as I showed you earlier, we're gonna call the release when we are randomly selecting a block to be released, and we know which block to release, then we're gonna call the release function. The release function does the following. First, it goes to the blocks array, and the index that is passed to it becomes the index of this array. We set the release to 1 because we are going to release that block. It was occupied, now it's going to become released. We are going to get the start address of that block that we are going to release it. We call it the start address. That would be block address, brackets block index dot address. We're going to get the size from this structure of blocks brackets block index dot size. And then the end address would be always the start address plus size plus 3. Again, I told you before why plus 3, because there are 2 dummy cells and a size at the beginning. So we're gonna just skip 3 more addresses to get to the end address. Now I have the start address and an address of the block that I'm going to release. It's time to find the left neighbor and right neighbor of your block. The left neighbor would be either 0. If your start address is 0, that means there is no left neighbor. So 0 basically is a sign that your left neighbor doesn't exist, right? And otherwise, it's going to be the memory at index start address minus 1. If the left neighbor exists, I'm going to represent it with its size. Why? Because when I get the size of a neighbor or size of a block, the sign of that size represents whether it's a whole or it's a occupied block. So the sign specifies whether it's a whole or a block, and the absolute value represents the size. So I can get all the information I want from the left neighbor by just reading this cell, which is the start address minus 1. So remember, the start address was, let me use a annotation. So this is the block that you want to release. This is the start address, this is the end address. The cell right before that would be your left neighbor's So this is your start address. The end address would be here. This highlighted cell would be your left neighbor. So the left neighbor is basically the value stored in this. The right neighbor would be the value stored right after this, which is here, right? The other highlighted one. That would be your right neighbor. Again, using the sign, you know whether it's whole or block, and using the absolute value, you know it's the size. And if the end address is n-1, then the right neighbor doesn't exist because your block is at the very end. So just represent your right neighbor with 0. Right? So we use 0 to show that the left or right neighbor don't exist. Now, if you want to release a block, I have printed, we're going to release this block with a certain left and certain right, so that, you know, you look at this and find out what's going on. That's good for your debugging purposes, but if you want, you can just comment it out. This is how you do it. There are 4 different scenarios. The first scenario, which is, I would say, the easiest one, is when you have no, I mean, it's not easiest, but it's like the most straightforward one. When you have no left hole and right hole, that means your left neighbor is occupied, your right neighbor is occupied. So that means when you're releasing the current block, you're going to create a new hole, right? It's not going to be combined with any other hole. You're just going to add a hole to the linked list of all the holes from this address to this address. That would be a hole. What is add hole? I'll show you the add hole later. Otherwise, if the left neighbor is a hole and the right neighbor is not a hole, negative means hole, positive means occupied block, and 0 means it doesn't exist. Doesn't really matter. If it doesn't exist also, you can assume it's occupied. So if the left neighbor is a hole, but the right neighbor is not, you need to coalesce the left neighbor and the current block into a bigger whole. Right? So you're merging or combining the left neighbor and current block into a bigger whole. The left coalesce is designed to do that. If the left neighbor is a block, but the right neighbor is a hole, then you need to call the right coalesce, which is going to get the 2 addresses, the start and end address of the current hole, and it's going to combine or coalesce the current block that we're going to release and the right neighbor, which is a hole, into a bigger hole, right? And in the 4th scenario, when both neighbors are holes, that means both left and right are negative. Then you need to do double coalesce. That means you're going to coalesce the left neighbor, the current block that is going to become a hole, and the right neighbor, which is a hole. You're going to combine them all into a bigger hole, right? So that's how this release looks like. Let me go over the first 3 functions: add hole, left coalesce, and right coalesce. You're going to do the last one yourself. If you see the left and right coalesce, writing double coalesce is pretty easy. It's just like a combination of these 2. Let me show you the add hole first. That's pretty much the first scenario when you're just going to create a new hole. How do you do this? Your start address and end address should be negated. Why? Because this block was representing an occupied block, now it's a hole. So the size should be negated because in holes, size are negative. So that's the first thing you need to do. Then you need to say, let me find out the next hole or the hole right after the current block So I can basically use that to join to the linked list of all the holes. So let's start the next hole. I set it to 0, but we're going to change that. The next hole is going to be updated. We're going to create a temporary index. That would be the end address plus 1. End address plus 1 is the beginning of the next block or the beginning of the right neighbor. In this infinite while loop, I will check the temp value and compare it with the following values. I will say if temp is greater or equal to n, that means we are going out of bounds. So start from 0 because you need to go all the way back and start over. That's a complete loop. You need to go all the way back to the beginning. Set the temp to 0 and then try again. Otherwise, if the memory at index temp is negative, that means if the temp is a hole, if temp points to the hole, that means congratulations, you have found the next hole after the current block, and that would be your next hole, right? And then you can break out of this while loop because you're done, right? You found the next hole. Otherwise, you're going to move forward. If it's a block, if it's not negative, that means it's positive, then it's a block. So you need to go forward and see the next one, see if it's a hole or a block. Temp plus equal memory temp plus 4. This is the size of a block. This is the metadata that the block contains. You need to add your temp with the sum of all of these and try again. That would be the next location and see if the next block is a hole or it's an occupied block. This while loop is going to eventually break. When you break out of that, you have the address of next hole. So you have to store that in your memory start address plus 2. That's basically the current hole next. Current hole next pointer would be the next hole. Then you have to find out the previous hole. The previous hole is not that difficult because in order to find out the previous hole, you can use the fact that your linked list is a double linked list. So what you can do is go to the next hole's previous reference, and that would be the previous hole. So next hole previous reference would be memory next hole plus 1. That would be your previous hole. And now that you have previous hole address, you can store it in memory of a start address plus 1. So now you have successfully set your next and previous references of the current hole. So you're almost done. The only remaining things that you need to do is go to the next hole and set its previous to the start address of the current hole, and go to the previous hole and set its next reference to the start address. If you want to make things a lot easier for you to understand, you can replace 1 by previous like this, and 2 by next. So it kind of have a better visuals, right? So that's kind of look better if you want to make your program a little bit more readable. So in other words, here you need to go to the allocator and say, let's define previous to be 1, define next to be 2, and that's pretty much it. If you want to do a little readability improvement, but without that, everything looks good as well. All right, so this is the add hole function. The other 2 functions that I wanted to show you, left coalesce and right coalesce. Left coalesce is just making the left neighbor bigger. How? It first finds out the left neighbor's end address, which is the start address of the current block -1. Then it tries to find out the start address of the left neighbor, which is going to be left address -3 plus memory of left end address, which is going to be the negation of the address of the left neighbor. Then it's going to print a message on the console saying we're left coalescing, combining these two blocks into one big whole. Left start address, left end address, start address, and end address. This is just for extra information. And then we are going to update the negation of size for the left neighbor. That's gonna become more negative. The size increase in the whole would be end minus start plus 1. And then because the left and current blocks will combine into a big whole, the end address of the resulting whole, or the bigger whole, would be the end address of the current block, and that should be equal to the size of the bigger whole, which is memory of left start address. Don't touch the previous or next reference of the previous or don't change the previous or next reference of the left neighbor, because we didn't change the structure of the linked list. So that's it. That's the easiest way of coalescing when you're doing left coalesce. When you do the right coalesce, it becomes a little trickier because you need to change the previous and next references of a few or at least one node. You need to say the right start address is going to be end address plus 1. Because remember, when you're doing right coalesce, the right neighbor is a whole. So its a start address would be end address of the current block plus 1. The right end address would be the right start address plus 3 minus this, which is going to be the negation of the size of the right neighbor, which was a whole. When you do the negation, become positive. It's like adding the size by 3 and then add it again by the right start address to get the end address. Now that you have the start end address of the right neighbor, it's time to, let's say, print out, we're coalescing these two blocks into a bigger one, into a bigger whole. Imagine when you're doing that coalescing, the size which is stored in the right end address should become more negative. By how much? End address minus address plus 1. That's the size of the current address, including those 4 bytes for the metadata. Then you need to say, all right, this size has to be stored in the first cell of the combined wholes. What's the first cell of the combined two wholes, the current whole and the next whole? That would be the start address. So you're going to store the negation of size of the both wholes into the start address. Also, again, you can simply say previous here. Also, you can say the memory start address plus previous. That means the whole before these two wholes would be memory right start address plus previous. That would be 1, right? And so that basically means now the two combined wholes have the same previous, but you have to store it in the current block's previous cell. And then the memory start cell plus next, or 2 means next, would be right start address plus next. Again, next and previous are basically 2 and 1, so you don't really need to change them. All right. That would be your right coalesce. Double coalesce, I just sent an error saying it's not implemented, but I want you to make your hand dirty and just look at the left and right coalesce and just combine them together and create double coalesce. In this function, all you need to do is to basically merge three holes into one. Um, just to give you a quick hint, so this is the current one with the start address that is given and the end address that is given, right? Let me grab them from the other location. Let's say this is the start address and this is the end address. Now I'm going to show you how to coalesce this one with the left neighbor, which is a hole, and the right neighbor, which is another hole, right? How do you combine these two? All you need to do is update this size to be equal to the size of the whole block, update this size to be equal to the size of the whole block. But remember, you need to store the negative value. So you need to store the negation of the size. So if the size of the combined whole is 100, you need to store -100 and -100 here and here. So these final cells should store -100 and -100 when you're doing double coalescing. And then there are two pointers here. One pointer here, that's the next hole, and one is here, that's the previous hole. I'm gonna call it P, which stands for previous, and N, which stands for next. Leave P as is. As long as it's not pointing to the next one. So P should basically be whatever it is, except if P points to the next one. That only happens when you only have two holes in the whole memory. That's very rare, but yeah, you may want to check that. So P should remain the same almost all the time, but except for an exceptional scenario. And next should be equal to the next of the next hole. So in the next hole, we have again a previous, this is the size, and then you have the previous, and then you have the next. The next reference of all three holes combined should be equal to this next. So you need to copy this into the next of the first hole. And when the size of the first hole is covering the whole thing, that means you have created a hole covering all the three blocks. The left neighbor, the right neighbor, and the current one. So all you need to do is to change the P or the N. P would not be updated most of the time, but N should be definitely updated. Becomes the next stop then, the right neighbor. So that's pretty much what you need to do. Other than that, everything else is done. For the first fit, you need to do the other algorithms. Let me run this and show you how it works. So this is the ocelot. I'm gonna first compile it, gcc-o allocator, allocator.c first fit.c -i-w-lm. Please use a makefile, but you need -lm because there are some mathematical operations. You need -i dot because there's an h file and so on and so forth. And after you compile it, then you can simply run it. I have some simple runs, like set the time, the n to 10,000, d is 200, v is 50, and x is 5. That means I'm going to run 5 rounds with this 10K memory, where the request average is 200 and the standard deviation is 50. At the end, it's going to calculate the average memory utilization to 92%, and then the average number of examined holes is going to be 14. But it's possible that you run it and you get to this error, double coalescing not implemented, because I haven't completed it, but double coalescing happens very rarely. Let me run it again. Next time you got similar numbers. Next time you get similar numbers, but if you run it long enough, you will get into an error saying double coalescing is not implemented. I didn't get that, but if you want to increase the number of rounds from 5 to 50, you definitely will see that. It says double coalescing is not implemented, so you need to implement that the way I told you, all right? And here, all the messages that I mentioned before are printed. You can just get to them, all of them, and then you only print um, these two messages at the end. What's the average memory utilization for first bit? What's the average number of examining holes for first bit? And do the same thing for the other 3 algorithms if you want to implement all of them and get 40% extra credit. Well, that's pretty much it. Thank you and have a good day.